Hi everyone, so let's suppose we had a problem that looks like this. So when will the sled stop? A sledder starts from rest, slides down a 10-meter high hill. At the bottom of the hill is a long horizontal patch of rough snow. The hill is nearly frictionless, but the coefficient of friction between the sled and the rough snow at the bottom is 0.3. How far will the sled slide along the rough patch? All right. So just noting down a couple things we know. We're told the height of the hill, that's 10 meters. We're also told that the coefficient of friction and the rough snow is 0.3. And we're not told much else. Alright, so we don't really know much information here. One thing to note is we're not given mass, so we're going to hope that cancels out, and in fact it will. Now we have to think about how we can approach solving this problem. So two different methods come to mind. One would be going back to kinematics. We could use kinematics to solve this problem. We could figure out the acceleration of the sledder down the hill. Well, one thing we're told, actually it's kind of interesting, we're not told whether this hill is a constant slope or not. So maybe we can't use kinematics. If we knew that, then we could, because the acceleration down the incline would be constant, and we'd be good to go. But that would not be the case if the hill was curved. But nonetheless, we could use kinematics to solve to deal with the part where there is friction along the rough surface, because the object's moving horizontally there. That force of friction is constant, so I have a constant acceleration there. So we might be actually put into a corner here and forced to use energy principles, because energy principles, it doesn't matter the path that our object takes down the hill, because the hill's frictionless. If there was friction, that'd be kind of annoying. But we're lucky here. And it doesn't matter the shape of the hill. So we're going to use work and energy to solve this problem. So let's kind of sketch out what's going on here. So we have some sort of hill. All right, I'm actually going to draw it like this. And then we have some amount of distance here. All right, so a couple different things in the problem. So we know our person starts off at the top of the hill. So maybe I'll call that our initial spot. So looking at this problem, right, hopefully you can identify we kind of have two parts to it. All right, so we know information about the top of the hill. We know the sledder starts at rest, and we know the height. Right. We also know some information about the bottom of the hill. We know that the sledder will be moving at the bottom of the hill, and at the bottom of the hill we have a height of 0. And then we know information about the rough patch here. Right, we know the coefficient during that. And we want to find how far the sledder will go. So maybe that spot there happens to be it. We want to find what that spot is. All right, so we kind of have two parts to this. We have the part of traveling down the hill, and then we have the part of traveling along the rough surface. Now, in order to find how far the sledder will go, and we'll be applying work-energy principles, at the bottom of the hill, we would need to know information about the initial kinetic energy right at the bottom of the hill. Which would mean we need to know the speed at the bottom of the hill. Now, in order to solve that, we need to then use information we know about the hill itself, applying work energy there to find the speed at the bottom of the hill. So let's do that here. So our plan right now is we're going to find an expression for the speed at the bottom of the hill, and then using that speed, then we'll use that to find how far our object's going to go. All right, so looking at the hill part of our problem. Let's sketching out a free body diagram. All right, we've got normal force perpendicular to our surface and force of gravity straight down. All right, no other forces, there's no friction. All right, so there's our free body diagram. So looking at how we define our system, it'd be ideal to make as many of these forces internal as practical as possible. So we definitely need the sled in our system, since that's the object we're analyzing. And we should also put the Earth in our system. Defining our system that way, when we look at our internal forces, the force of gravity is internal, because that's an interaction between the sled and the Earth. So gravity is an internal force, and external forces, we've got our normal force. Right. Now we're okay with the normal force being external, because our sled is displacing down the incline. So since our sled's moving down the incline, the normal force is perpendicular to that. So even if the slope of this incline is changing, the normal force is still going to be perpendicular to the instantaneous displacement at that spot. All right. So when we're applying our work energy theorem, work is equal to change in energy, we're dealing with work done by external forces. So this is the work done by our normal force, is equal to change in energy of our system. All right, so we always have to worry about kinetic energy, so change in kinetic. And then looking at internal forces, we've got force of gravity, so we need to worry about our change in gravitational potential energy. So for looking at the hill, we'll call our initial at the top of the hill, and our final the bottom of the hill. All right, so going back to our work energy equation, work done by the normal force, we said that's 0 because the normal force is perpendicular to our displacement, so it does no work. So our system here is actually isolated. Now looking at our change in kinetic energy, so we have 0 is equal to, can you see this? You can, we're kind of reaching the bottom of this. All right, so 0 is equal to final kinetic minus initial kinetic plus final gravitational potential minus initial gravitational potential. Plugging any zeros here, well, we know our object starts at rest, so initial kinetic energy is 0. And let's define the bottom of the incline to be our 0 height, so its final height is 0. So moving along here, we've got 0 is equal to final kinetic energy minus initial gravitational potential energy. So we have our initial gravitational potential energy is equal to final kinetic. So this is mg times our initial height. We'll write that as y initial is equal to our final kinetic 1/2 m vf squared. M's cancel out. That's very convenient. Right now we're trying to find that speed. And so then our final speed, at the bottom of the hill, is equal to the square root of 2g times our initial height. So I'll just write that as h since it's how I define my variable. We could plug things in here. All right, we could plug in the gravitational acceleration, the 9.8 meters per second squared or 10 meters per second squared, depending on what tickles your fancy, and then our height being 10 meters. If we did this, we would end up with a value of about 14 meters per second. I'm not going to plug this in yet. I'm just going to keep this expression till the end. Because now we're going to use this information. This is now our initial speed along rough surface. So looking at our rough surface, all right, so now we've kind of got our second part of this problem. Drawing a free body diagram for our sled, we've got normal force upward, force of gravity downward, and then we've got friction. Well, our object's moving to the right, so friction is going to be the opposite direction then. Force of friction. I'll kind of write off to the side here to note our displacement of our object is rightward. Our object's moving to the right. Okay, defining our system. Alright, so we want to make as many of these forces here internal as practical as possible. So our system, we definitely need the sled. Force of friction, we cannot make internal. We don't really have a means of solving a problem that way. It's a non-conservative force. We can't have it be in our system. So the surface is not in our system. Let's see, normal force and gravity. We do not need to include the surface or the earth in our system because those are going to be perpendicular to our displacements. The work done by them is 0. So actually here, long story short, we're going to make our system just the sled. All right? So therefore, listing internal forces, there are none. External forces, sorry, I keep having that pop up. External forces are all of them. So we have the force of gravity being external, the normal force being external, and the force of friction. So now when we apply our work energy theorem, all right, so the work's done by external forces. This is the work done by gravity, plus the work done by normal force, plus the work done by friction, is equal to change in energy. So we always worry about kinetic, And since we don't have any internal forces, we don't have any other types of energies we have to be concerned with. It's just kinetic energy. We realize here that the work done by normal force and gravity are 0 because they are perpendicular to the displacement of the object, so those forces don't do any work. So we just have the work done by the friction force. So remember that the formula for work is Fd cosine theta. So since we're concerned with friction, it's the force of friction times the displacement of our object times cosine theta. Now the thing to realize here is this displacement d is what we're trying to find in the problem. The problem asks for us to find how far the sled slides along the rough patch. Well, that is this displacement d. So we'll be solving for that. And that's equal to our change in kinetic energy. So our final kinetic minus our initial kinetic. Seeing if any of these things are 0 here, or any other convenient things to plug in. It's going to be convenient to plug in force of friction. We know is going to be mu times normal force, right? We have to do that since mu is what we're given. You can also plug in that our angle here is 180 degrees because our displacement's rightward, force of friction is leftward, so the angle between them is 180. We can also realize that our object is only going to go as far as it can, which means its final speed is going to be 0, so its final kinetic energy is 0. So simplifying here, we've got mu times normal force. Looking at our free body diagram, normal force is equal to the weight, mg. So you have mu, mg, displacement, cosine of 180 is -1. So this is negative, is equal to 0 minus our initial kinetic energy, 1/2 mv squared. I'm not going to put a subscript on the v. Alright, let me scroll here. Our negative signs cancel out. We are solving for d. I'm going to plug in my expression for the speed. Speed is the square root of 2gh, so v squared is just going to be 2gh. So we have mu mg d is equal to 1/2. Oh, our m's cancel out. Let me take care of that now. So negative mu g d is equal to, negative 1/2 v squared, so it's 1/2 times 2gh. So the 1/2 2 cancels out. So then our displacement is going to be gh divided by, our g's cancel out too. So let's get rid of that. So we've got h divided by mu times d. Don't know why I divided by d there. It's funny because I was just looking at my answer and I'm like, oh, that doesn't make sense. I'm taking height divided by distance, so my right-hand side was unitless, where I needed to have a value of distance. So, good thing I checked to see if my answer makes sense. So what I'm doing here is now taking our height, which is 10 meters, and dividing by mu, which is 0.3. So 10 divided by 0.3, that just ends up being about 33 meters. So that's how far our object will go. Alright, so the second part here, we could have used kinematics. I frankly find energy principles a little bit easier to use. A lot of times the problem will dictate how you're going to be forced to solve the problem. So odds are I'm going to tell you to use work energy or apply the work energy theorem to solve whatever problems you need to during this unit, since the whole point of this unit is practicing solving these problems. But on the AP exam, if they don't specify what method you can use whatever method is appropriate. If acceleration is constant, you can either use energy principles or the or kinematics to solve. Right? So hopefully that was helpful.